Hello, myself is Prem Chandra and my thesis has been completed from IIT Bombay. And today I will teach a very important topic for the CSR NET and GATE exam. And this topic is a function of sequence of function. And sequence of function, either we can say that uniform convergence. So see that the first one is this is summary of the uniform convergence. So only I will teach in this lecture the summary of the uniform convergence. So see that in this summary how will apply in the question. So see that the second one is now pointwise convergent. So this point-wise convergence. So firstly I will define what is point-wise convergent. So first I will write the definition of the point-wise convergent. So first, given f n x. So here given f n x is we sequence a function. So given f n x. So here f n x is a sequence of function. Sequence of function. That sequence of function defined in one interval. Say that for all x belongs to interval, say that I end for all n belongs to natural number. So this is a sequence of function. So in this sequence of function we will find the limit, and you can find the limit f n x n tends to infinite. Whenever you can take the limit n tends to infinite, you will get again some function. So see that as function is f of x. So f of x is a function. This is f of x. See that whenever you are going to the n tends to infinite, f n x going to the f of x. That means here given the f1, f2 dot fn, and all are fn, whenever n going to the infinite, after some n naught we will go to the fx. That means, that is what is meaning. Meaning is for all epsilon greater than 0, there exists n naught belongs to natural number. This is again definition you can write such that mod of f n x minus f of x. So firstly you can say that the definition of this whenever n going to the infinite, this fx. So f of f n x going minus f of x less than epsilon for all n greater or equal to n naught. So whenever any sequence of function converge to the fx, that meaning for all x belongs to I, we will get, whenever you can put x belongs to I, in particular x naught put in fn x naught. So fn x naught is, whenever put any x naught, so fn x naught is again sequence of real number. This is a sequence of real number. This is not a sequence of function. Okay, so whenever you can put it at any value of x naught in this fn x naught, so you will get this is a sequence of real number. So every sequence of real number for all x belongs to I, this is convergent. So that sequence, whenever put any value of x belongs to I in this sequence of function, you will get the sequence of real number. If every sequence of the real number in the whole interval x belongs to I, this is convergent, then this is called the pointwise convergent. So that type of sequence is called the pointwise convergent. That meaning is simple meaning, nothing is special. Whenever you can put the x any value in this interval, in this sequence, you will get the sequence of the real number. So we will go to the sequence of real number. So it's sequence of real number. So every sequence of real number for all x belongs to I, this is a convergent. Then this sequence of function is called the pointwise convergent. Definition is the same. Because whenever you go to the sequence, so sequence also we can write the xn minus x less than epsilon for all n greater or equal to n naught. But there is a sequence of real number, so x is again real number. But here is a function, so fn x minus fx less than epsilon for all n greater or equal to n naught. And such fx, this fx, that means that fx is called the limit of function. This limit of function, that sequence, that a function fx called the limit of function of the sequence of function. So this is called the limit of function. So see that now. Next one, see that uniform convergent. So uniform convergent. See that what is the difference between the pointwise convergent and uniform convergent? Only one small difference in the pointwise convergent. In the first definition, whenever I will write the definition is given So definition is I will write the definition f of x. So see that f of x is, so f of x, I will write definition f nx minus f of x mod less than epsilon. But that I'm not saying that a particular sum of epsilon. I'm saying that for all epsilon greater than 0 and there exists n naught belongs to natural number. But now for all n greater or equal to n naught, that definition, the definition is hold, then this is also called the uniform convergence. So see that what is the difference between the pointwise convergent and what is the difference between the uniform convergent. So only one difference here, this n naught depend on only epsilon, but back definition I will not write this n naught depend on epsilon. Maybe n naught depend on epsilon as well as point, but in this definition particular sequence of function only depends on this n naught depends on only epsilon, and such sequence of function is called uniform convergence. So whenever given any sequence of nx, firstly you can see that this sequence is pointwise convergent. After that, whenever you can find fx, this limit of function, you can apply the definition f nx minus fx less than epsilon, and you can find for all epsilon you can find the n naught. If this n naught depend on only epsilon, then this type of function, this type of sequence of function is called uniform convergence. So this is a small difference between the pointwise convergent and uniform convergent, and very small difference. Only n naught depend on epsilon, and the back definition n naught depend on epsilon and as well as x is also. So if any next one is, so next one uniform convergence theorem. So you can see that how will prove that f and x is uniform convergence, because sometimes given sequence of function you cannot find generally n naught, and this n naught depend on the epsilon, because very difficult task to find the n naught. So sometimes you cannot find the n naught, then how will show that this sequence, given sequence of function is uniform convergence or not. So here I will give the one theorem. Theorem is uniform convergence theorem, because here I will not prove that any sequence, because I will write the only summary of the sequence of function. So whenever I will prove that, so see that how will prove that this one is sequence this uniform convergence theorem is true or not. So first, what is uniform convergence theorem? See that the statement is, given statement f and x be the sequence of function such that limit n tends to infinite f and x is equal to fx for all x belongs to a comma b. So this is a given sequence of function for all x comma belongs to a. So this is a sequence of function. So sequence of function, first see that fx. Okay, so this sequence of function has pointwise convergence. First one, pointwise convergence for all x belongs to ab. Now suppose let the supremum f n x minus f for all x belongs to I. You can find the supremum of f n x minus f. You can find the supremum of that term f n x minus fx. Whenever you can find the supremum of f n x minus fx, then after then what is the statement of theorem? Theorem saying that if then f and x converge uniformly to f on f, if and only if, and that theorem is very important because the theorem is written as if and only if, the both side true. If such equation is hold, mn tends to 0 as n tends to infinite. Whenever mn you can find mn, and mn you can find that mn is the supremum of that one. This mn going to the 0 as n tends to infinite. Whenever such condition is hold for any sequence of function, then this sequence of function is called uniform convergence. If we can find such mn and mn not equal to 0, I am saying that this sequence of function is not a uniform convergent. So this theorem is very important theorem, because this theorem is written as if and only if the both condition is hold. If mn going to the 0, then sequence of function is uniform convergence. If mn not going to the 0, then I'm saying that sequence of function is not uniform convergence. So sometimes you can use the very easily non-uniform criteria for the sequence of function. Okay, so now next one is, so next sometimes I will use the given sequence of function and I will use the interchange of the limit of function. Also sometimes given limit of function, if limit of function is a continuous if not continuous, if not bounded, if not differentiable, not integrable, then you can say that also this sequence of function is non-uniform convergence. So how will apply this criteria? So interchange of limit of function, sometimes the limit of function is not continuous, then how will say that given sequence of function is non-uniform convergence. Sometimes is not differentiable, then how will say that given sequence of function is non-uniform convergence. Sometimes integrability is also we will use, and sometimes we will also use the boundedness. So see that number 1 theorem, number 2 theorem, how will use this all theorems in this sequence of function, and you will show that given sequence of function is uniform convergence. So very important theorem. Sometimes given sequence of function, but we cannot say that this sequence of function is uniform convergence or not. So how we check? So firstly, I will apply this given sequence of function is a non-uniform convergence criteria, because non-uniform convergence criteria you can use the limit of function is continuous, not bounded, not differentiable, not integrable. So see that the next theorem how will apply in the sequence of function. The theorem next one. So theorem is if Fn is a sequence of continuous function. So see that is very important condition is first one, Fn given, the sequence of function is given and that sequence of function is a continuous function. So see that now given sequence of function, I am saying that given sequence of function is a continuous. See then Fn, this is given sequence of function, this is sequence of function is continuous. This is my first condition. All are continuous, that means f1, f2, fn, and dot infinite. All are sequence of functions are continuous and uniformly converge to the f. And uniformly converge to the f. Here we can write the uniformly converge to the f. I am saying that given the two condition. Which one? Number 1, given sequence of function is continuous, and number 2, that sequence of function is also uniform convergence. So whenever such two condition is hold, you can find the fx, then you can say that anything about the fx. So this f is also continuous. This is theorem. Theorem is saying that whenever given fnx is continuous and fnx is uniform convergent, then limit of function f is also continuous function. Now how will use of this theorem? So theorem we will use whenever given sequence of function is continuous and you can find this f. If f is not continuous, your fn is not a uniform convergent. So here I will write the if limit of function is not continuous, if limit of function is not continuous and given sequence of function, here I will not write, but listen very careful. First one, given fnx is continuous, all are fnx continuous for all x belongs to I, given interval this fnx is a continuous, and now limit of function is not continuous in the whole interval. If limit of function is not continuous and given sequence of function is continuous, surely we will say that by this theorem, this sequence of function is not a uniform convergence. So sometimes given sequence of function we will use that theorem, and the theorem is very important because sometimes given sequence of function we can find the limit of function. So whenever you can find the limit of function, you can check the limit of function is continuous or not. If the given function sequence of function is continuous, we can prove that very easily the fnx is non-uniform convergent. Okay, now next next one, differentiability. But you cannot say that very easily. This condition fn be the sequence of differentiable function converge to uniformly, then function may or may not be the differentiable. In the back theory, I am saying that whenever given sequence of function continuous and fnx is uniform convergent, I am saying that limit of function is continuous. But in this theorem, I have some problem. Problem is given sequence of function is differentiable and given sequence of function is also uniform convergent. But fx may or may not be differentiable. So I will write also example, and this example is very important example because Weierstrass comes and gives such example. Weierstrass fx is equal to this one is a continuous at everywhere but not differentiable at any point in the whole R. Weierstrass comes and gives the very interesting example in the whole real number. Such example is a continuous in the whole real number but not a differentiable in any point in the whole real number. But now we can construct a sequence of function. So how will construct? See that I will write the y considering partial sum of the series. Why consider partial sum of the series? Whenever you can take the partial sum of the series, see that partial sum is a sequence. So obtain the sequence of function fn. Whenever you can obtain the sequence of function fn, because you can find 0 to n or n minus 1. So this is a finite set. So this is a differentiable. So fnx is a differentiable. But whenever you can take n tends to infinite, you will get that sequence of function. But this fx is not a differentiable. So how will use that criteria for the differentiability? So differentiable function uniform convergent, but if it's not a differentiable. So if f is not differentiable, we will not write in this way. Limit n tends to infinite d over dx fnx. You cannot interchange limit and sequence of function, limit and differentiability. You cannot interchange if fx is differentiable and f is uniform convergent. But if fn dash is uniform convergent, then all is well. I have one extra condition. Whenever given fnx is uniform convergent or not, but the derivative of fn dash, maybe fnx is differentiable and fn dash is a uniform convergent, then surely f is a differentiable. So see that the next one. Okay, so fn is a pointwise convergent to the f. So I have one extra condition, the theorem number 2. This is say that theorem 2, fn is the pointwise convergent to the f and fn dash is uniformly convergent to the z. Given sequence of function is only pointwise convergent. I am not saying that this is a uniform convergent or not, but is this given sequence is only pointwise convergent and the derivative of the sequence of function is converged to the z, then sure fn is converged to the uniformly and f dash, if this is converged to the f, then f dash is equal to z. Yes, or you can see that very careful. I am not saying that this is the only pointwise convergent to the f. Also I have some extra condition. If fn x not is uniform convergent, if convergent, that means this fn given sequence of function is only convergent at only one point, and fn dash is uniform convergent and fnx is differentiable, then surely we know that fx is limit of function is differentiable function, and also the derivative of the limit of function is equal to z, and also you can interchange the limit and fn and d over dx is the limit of fnx. So you can interchange the difference derivative and the limit function. Whenever fnx convergent at one point, fn dash is uniform convergent and fn is differentiable, then you can interchange that limit and derivative of function. So you can see that the next one. So how will use that one? You can use whenever given sequence of function, we will get the fnx is f and fn differentiable and z is not a differentiable, then we cannot say that uniform convergent. So now next one is now what is use of the integrability? What is use of the Riemann integrable? So fn is a sequence of the integrable function. Also you can write the Riemann integrable function and converges to the f, then limit of function need not happen. If only convergent comes in the sequence of function, we cannot say that anything about the limit of function. Maybe f is integrable, may not be f is integrable, and also that we cannot happen. You cannot interchange the limit and integration if that condition is to hold. If but fnx is a Riemann integrable and I will write fn is a sequence of the Riemann integrable function and uniformly converge to f. So given sequence of function is a Riemann integrable. Number 2, satisfy fn is uniform convergent to the f, then surely f is integrable. So how will you use this theorem? You can use this theorem whenever given fnx is a Riemann integrable. You can find the limit of function. If the limit of function is not a Riemann integrable in the I, then surely fnx is not a uniform convergent. And this theorem is also very important to show that fnx is a non-uniform convergent. Okay, so now see that next one is next one is a Dini's theorem. Suppose fn is a monotonic sequence of the continuous function. So Dini's theorem saying that how will prove that given sequence of function is uniform convergent. So see that what is Dini's theorem. Suppose fn is a monotonic sequence of continuous function. First condition is a monotonic. Second condition is continuous on I but closed interval I and converges to I in the continuous function. And the limit of function, those who are limit of function is also a continuous function. Then sure fnx is uniform convergent. I have some condition in fnx is monotonic, fnx is continuous and continuous on the closed interval AB, and also that limit of function is also continuous, then we can say that sequence of function is uniform convergent. Okay, so now in the back theorem you can see that how will interchange the integration and limit. You can interchange limit and integration whenever given sequence of function is integrable and fnx is uniform convergent, then you can interchange the limit and integration. But also you can use another theorem. I will say that another theorem is fnx is a Riemann integrable. Yes, very careful, you can listen. Fnx is a Riemann integrable and fnx is a bounded. Fnx is a Riemann integrable and fnx is bounded, and fx means limit of function is also Riemann integrable, then you can also interchange the integration and limit of function. This is theorem. This theorem is also very important because sometimes you cannot show that fnx is uniform convergent or not, but if you show that this fnx is a bounded and fnx is a Riemann integrable and also limit of function is a Riemann integrable, you can say that you can interchange the limit and integration also you can change very easily. Okay, so sometimes you cannot show that very easily uniform convergency, then you can also interchange the limit and integration. So now next one, see that. Okay, so this was last theorem. So this is whole summary of the sequence of function. This was a whole theory of the sequence of function, and you can enjoy surely those who are interested to join the CSR NET and GATE West for the mathematics. You can contact with 7905390716 for the classroom program, also live classroom program. So classroom program and online class program, and you can enjoy this mathematics in the JEE Institute Kanpur. So those who are interested to offline classes, you can come in the Kanpur. This is the Kanpur branch, JEE Institute. Thank you all. Thank you very much.